Let's solve Unit 7 Data Structures and Algorithms questions, which is a self-balancing binary search tree where the path from the root to the furthest leaf is no more than twice as long as the path from the root to nearest leaf. Just by looking at the option and the syllabus, you can find the answer is going to be red-black tree. So there are two parameters here, root to the nearest leaf and root to the furthest leaf, and they say the path is no more than twice, so it is less than or equal to 2 times of the path from the root to the nearest leaf. Self-balancing binary search trees always maintain height to a minimum. The balance factor is given by the difference of left subtree height and the right subtree height. Such trees perform rotations after execution of an insert or delete operation. So after we insert an element or delete an element, rotations will be performed in order to maintain that particular balance factor. The examples of self-balancing binary search trees are listed here. We have 2-3 tree, red-black tree, AA tree, aviate tree, B tree, scapegoat tree, splay tree, tango tree, treep tree and weight balance trees. Some are taken from reference books, some are taken from web source. So I would like to concentrate on few trees here. The red-black tree is what we can say the path from the root to the farthest leaf is no more than twice as long as the path from the root to the nearest leaf. So this statement is exactly belonging to red-black tree. So we can mark option 3 as the right answer. AA trees are left-leaning red-black trees after a symmetric reformulation. It means they work with different rebalancing algorithm. This is about the AA tree, and we know about AVL tree. The height of the left and right subtrees of any node will differ by 1 at most, so not more than that. And for scapegoat trees, the rebalance occurs whenever the size of a child exceeds a certain ratio of its parents. This ratio is known as alpha. Next question. Arrange the following steps in the correct order to solve the knapsack problem using dynamic programming. So we have already seen about knapsack problem in one of the previous year question paper. We have two kinds of knapsack problem. So one is called the fractional knapsack problem and the other one is the 0-1 knapsack problem. So in fractional knapsack we will be able to add a fraction of the item, but in 0-1 knapsack we either include the item or exclude the item. So this 0-1 knapsack problem is actually solved using dynamic programming technique. So the dynamic programming solution is required for 0-1 knapsack problem. The fractional knapsack problem is solved using the greedy approach. Now they are asking the correct order to solve this problem in dynamic programming. So let's look at the options first. Define the base case where the capacity is 0 or no items are left to consider. Compute the maximum value that can be obtained using items up to the ith item and a knapsack capacity of 0. Identify subproblems and their dependencies based on item weights and values. Initialize a table to store results of subproblems. Iterate through each item and each possible capacity to fill the table. So from C, D and E you can understand one thing. Only after identifying the subproblems you will be able to store the results of subproblems. So definitely after C we will have D, and they have told iterate through each item and each possible capacity to fill the table. Which table are they talking about? They are talking about the table that is being initialized in option D. So definitely E will be following D. In this case, just find the options which have the order of C, D and E. Only one option is having this order of C, D, E. Now we have to check between A and B. Define the base case where the capacity is 0. Initially the capacity will be 0. So the initial condition is what we have to start with. So we will be starting with A. Compute the maximum value that can be obtained using items up to the ith item and a knapsack capacity of 0. When will we compute the maximum value? We will compute it after adding the items to the knapsack. So this particular line can be taken as the final step. Now just arrange in this order. Define the base case when the capacity is 0. Identify sub-problems based on item weights and values. Now we are solving the sub-problem and we are storing it in a table. We are iterating through each item and each possible capacity to fill the table. So once you fill the table and you find these are the items that are going to be accommodated in the knapsack, we are computing the maximum value that can be obtained using items up to the ith item. What is this? A knapsack capacity of 0 is, imagine if the maximum capacity of the knapsack is going to be 20. Once you keep adding items, say for example you are adding 5, then 20 minus 5, the capacity will be 15. Then you are adding something to 10. 15 minus 10 will be 5. Then you are adding something with 5. 5 minus 5 will give you 0. So until this capacity becomes 0, you will be computing it again and again. So this is what they say, compute the maximum value that can be obtained using items up to some ith item, and the knapsack capacity should be 0. It means till that item you can accommodate, after that you cannot. So from where do you pick those items? Actually from this particular table. Where is the table initialized? It is initialized in D. For what it is initialized? It is initialized to store the results of the sub-problems. Where are we identifying the sub-problems? In C. This way also you can find the answer. Option number 3, A, C, D, E, B will be the right answer. Next question. Arrange the following recurrence relations in increasing order of their time capacity. So the relation is given, we have to compute the complexity, only then we will be able to arrange it in ascending order. To solve this problem, we are taking the help of Master's theorem. F of n is given in this form, and based on that they have given some time complexities. N is equal to B power k, where k is a positive integer, a is greater than or equal to 1, b is an integer greater than 1, and c and d are real numbers, with c positive and d non-negative. So this is c into n power d they have given, and all these are in the form of n power only. So 1 can be taken as n power 0, which is equal to 1. Then this is n power 1, which is equal to n. Similarly, root of n can be taken as n power 1 by 2. So everything is in this form only. Based on this, we are going to take the time complexity. Let's start with A. We have T of n is equal to T of n by 2 plus 1. This is in the form of n by b. So from this we can take the value of A to be 1, B to be 2. It is n by b. So we are comparing it with A of T into n by b. So we are just considering this to be A value and this to be B value. So based on that we are taking A is equal to 1, B is equal to 2. Here the function is given as 1. 1 means we know n power 0 is equal to 1. So what is this n power d? So here d is equal to 0. Now we have to check B power d and A. So A is equal to 1. What is B power d? It is 2 power 0, which is equal to 1. So A is equal to B power d. We are going with the second condition. What is the complexity? It is big O of n power d log n. So now we know the value of d is 0. What is n power 0? It is 1. So 1 into log n will give you big O of log n. So n power d will be n power 0, which is equal to 1. A option is giving big O of log n. What about B? We have T of n is equal to 2t n by 2 plus n. Here we know A is equal to 2. We have to take it from here. B is equal to 2 again. We have n power 1 here. N power 1 is equal to n. So from this we can compute d is equal to 1. What about B power d? We have 2 power 1, which is equal to 2. Again we have A is equal to B power d. So here we have to go with big O of n power d's value is 1, then log n. This will give you big O of n log n. So we can go with big O of n log n. What about C? T of n is equal to 3t n by 3 plus n. Here we have A is equal to 3, B is equal to 3, then n power 1 is equal to n, so d is equal to 1. So again B power d is equal to 3 power 1, which is equal to 3. A is equal to B power d. Here also we are ending with big O of n log n. So this is big O of n log n. So B can be followed by C and C can be followed by B. Regarding D, it is 2t n by 2 plus square root can be written as n to the power of 1 by 2. So A is equal to 2, B is equal to 2. And here we know D is equal to 1 by 2. It is actually 0.5 we can say. So definitely we know A is greater than 2 power 1 by 2. So root 2 will give a value that is less than 2. So this time we are going with A greater than B power D. So here it is big O of n log A to the base B. So what is log A here? Log 2 to the base 2. We know log 2 to the base 2 will be equal to 1. So this is big O of n power 1 which is equal to big O of n. So this is big O of n. What about E? T of n is equal to T of n minus 1 plus 1. So this is not in the form of Master's theorem. We have to take it in other way. Now how will you find T of n minus 1? T of n minus 1 can be taken as T of n minus 2 plus 1. Now we will substitute this T of n minus 1 here. So we have T of n minus 2 plus 1 and this plus 1 will be following here. So instead of n minus 1 I am just substituting the previous term. Similarly, what about T of n minus 2? We will have T of n minus 3 plus 1. So we will go with T of n minus 3 plus 1 for T of n minus 2. Then this plus 1 is from here and this plus 1 is from here. This is how we will be taking, and ultimately you will come to a place where T of 2 is equal to T of 1 plus 1 and T of 1 is equal to T of 0 plus 1. You are going for n number of terms. So in this case we can take this as big O of n. So you are not multiplying anything, you are just working with n number of terms. You can simply say T of n can be obtained by T of 1 plus n minus 1 terms. So here T of 1 we know the value is 1. So this is 1 plus n minus 1. You can just cancel them and then get n here. I am plainly taking it as n minus 1 terms. And we are bringing this to T of n is equal to n here. So this is just a working that they have given in order to justify how it is big O of n. We know B and C will be occurring together and D and E will be occurring together. What is the order of complexity actually? Log n will be less than n and it will be less than n log n. This is the actual order. So what is log n here? It is A. So we will have A first. What about n? We have D and E. So it can either be D or E. What about the n log n part? It is either B or C. So anything that ends in BC can be considered. We will rule out the other two. It should start with A. So the only option that ends with BC and starts with A is option 2. We go with option 2 as the right answer. So we have the order of E and D here. Now how are we arranging the order of ED and BC? A small explanation to that. We have seen one recurrence relation in this format. So whenever you have f of n is equal to big O of g of n, this will be like less than or equal to c into g of n. You will bring it to a form of constant into a particular function. Hope you remember this part. This c, when it is computed for b, the c value will be c into n by 2 plus n into log n by log 2. When you compute it for C, this will be C into n by 3 plus n into log n by log 3. When you divide a problem into 2 and you divide a problem into 3, based on this part, we are concluding that B is less than C. Similarly, when you take D, C into n by 2 plus root 2 into root 2 minus n divided by root 2 minus 2, and for E, C plus n. So from this we can say C plus n is less than, that is E is less than D. So how they have interpreted E is, when you want to take T of 1, it is T of 0 plus 1. This part is actually equated to a constant plus 1. If you take T of 2, it is actually T of 1 plus 1. So here it is C plus 1 plus 1, which is equal to C plus 2. So if you take T of 3, it will be C plus 3. If you take T of n, it will be C plus n. So this is how they are bringing E to the format of C plus n here. Next question. Select the sorting algorithms that are stable. What is a stable sorting algorithm? There will be a set of elements. If two elements are equal, their order will be preserved in the sorted output as it was in the input. What are the stable algorithms here? We have bubble sort, insertion sort, merge sort and counting sort. From this we will be able to mark B, insertion C and merge D. So B, C, D will be the right answer. Since no option is providing this answer, they have dropped this question in the official answer key. B and C can be right, but along with that, we also have merge sort as the answer. So that's why the question is dropped. What are the unstable algorithms? Quick sort, heap sort and shell sort can be treated as unstable algorithms. In quick sort, what we do is we actually split the array into two parts. One array will be greater than a particular pivot element and the other array will be lesser than the pivot element. Usually the leftmost element will be considered as the pivot element. The two sub-arrays are sorted by recursive calls to quick sort. In merge sort, the selection splits a list into two lists. Merging joins two files to make one file. In quick sort, it starts with the largest subfile and finishes with the small ones, and as a result, it needs a stack. This algorithm is not stable is what they try to say. When you take merge sort explanation, it starts with the small subfiles and finishes with the large one. So it does not need any stack. This algorithm is stable. Next question. Match list 1 with list 2. List 1 has recurrence relations and list 2 has complexity. B, A, D are from the question that is already solved. So let's take the difference between big O and theta now. Big O only gives an upper bound, which means it can describe the worst case. What about theta? It gives both an upper and lower bound, making it a tight bound. That is what we call as average case. Now let's take the Master's theorem that we saw previously, and along with that we have a Master's theorem. Here you can find the upper bound, lower bound and the average case. Now I am equating this f of n value based on this particular theorem. So f of n is equal to big O of g of n when a is less than or equal to b. When a is greater than or equal to b, we can mark it with omega. When a is equal to b, we can take it to be theta. So this is how I am mapping f of n's time complexity along with this particular Master's theorem based on the condition a greater than b or a less than b or a equal to b. Now let's take the first option. T of n is equal to 2t n by 2 plus n is actually n log n. We have found this already in the previous problem. This n log n can be taken as omega of n log n or theta of n log n with respect to this particular relation. They have given floor of. So this particular recurrence relation can be equated to any of the complexity. So we are mapping A to 1 directly. A1 is available in two options, so we are ruling out 2 and 4. What about B? T of n by 2 is given in seal notation. It means it can be taken to a higher level. Since seal is provided here, they have equated it to theta of n as exact solution. So B will be mapping to 3 here. Actually B's value will be big O of log n because you have T of n by 2. There is no doubt in that. But how they are equating it to option 3 in list 2 is what I am trying to tell you. So this is given in seal form and this is given in floor form. You need to note that. Floor of some value will give the small value here and seal of some value will give the large value here. So based on that they have done the working there. What about C? We have 2 into t n by 2 plus 1. From this we can take a is equal to 2, b is equal to 2, then n power 0 is equal to 1. So d is equal to 0. So 2 power 0 is 1. From this we can conclude a is greater than b power d. This part is coming. We have a greater than or equal to b. So we are using here omega symbol. It is big O of n log a is 2, b is 2. So log 2 to the base 2 will give you 1. This will be equal to big O of n power 1, which is equal to big O of n. So C is directly mapping to big O of n, which is in option 4 in list 2. So C4 is here and this is B3. So 3 of the options are matching. We can even rule out 1. What about D? Actually we know T of n is equal to t of n minus 1 plus 1 will give a complexity of big O of n only. But how are they mapping it to 2 here? Actually the question expression is wrong here. The actual recurrence relation should be t of n is equal to t of n minus 1 plus n. So instead of 1 it should be n. If that is the case, we can map d to 2 clearly. T of n minus 1 plus n will give a value of big O of n square. If you take t of n is equal to t of n minus 1 plus 1, this is definitely big O of n. But since it is plus n, it is big O of n square. Actually it's a printing mistake, but the answer is right. So except for D, if you take, the options are right with A1, B3 and C4. So they have not dropped this question. Option number 3 will be the right answer. So since we have already worked out A and B, I just took the answer as it is. C was new to this particular question. So I worked it out again using this particular f of n. Next question, match list 1 with list 2. So let's start with the list 2. Find the shortest path between all pairs of vertices in a graph with positive or negative edge weights. We know Floyd-Warshall algorithm is known as all pair shortest path algorithm. Keeping this as the clue, we can map B to 1. B1 is available in 2 options, so we can rule 3 and 4. What about the second one? Find the shortest path in a weighted graph with non-negative edge weights. This is purely for Dijkstra's algorithm. It works with positive edge weights. So we can map A to 2. So A to B1 is available in both the options. What about strongest connected component? If we can reach every vertex of a component from every other vertex in that component, then it is called a strongly connected component, where you can equate this. One vertex is there as a source. It can be connected to any other vertex. So this is actually bringing in the Bellman-Ford algorithm concept. Single source shortest path algorithm. So from a particular source, you can measure the shortest path to any other vertex is what they say. So in that way, C will be mapping to 4. But I am not mapping it as of now. Let's get on to the Prim's algorithm. Prim's algorithm starts with a single node and explores all the adjacent nodes with all the connecting edges at every step. Just look at the statement here. Sorts elements by repeatedly moving them post neighboring elements that are smaller. Though the statement is not directly reflecting, it is almost taking up the same meaning. So here we can map D to 3. Prim's algorithm will be taking the explanation in 3 here. So D3 is available here. So we can also rule out option 1. Now there are arguments stating that strongest connected components is an application of depth first search algorithm and not Bellman-Ford algorithm. Yes, it is true. Depth first search has 2 applications. One is topological sorting of a directed acyclic graph and decomposing a directed graph into its strongly connected components. So this is where we use DFS. When you take topological sorting, it is actually connected to Bellman-Ford algorithm. We can use topological sort on directed acyclic graph. This is what we are inferring from here. There is a variation of Bellman-Ford algorithm that can be applied to directed acyclic graph. The vertices are first topologically sorted and then the edges are relaxed in the order of the topologically sorted vertices. This is the mechanism that is happening within directed acyclic graphs when you use a variation of Bell-Manford algorithm. So just go with the reverse connect. You have DAG here. In DAG, you go for topological sorting. Using DAG, we are having an application of Bell-Manford algorithm, and this DAG is an application of DFS for what? For topological sorting of DAG as well as decomposing a directed graph into strongly connected components. So somewhere this is depending on strongly connected components, and that's why they are trying to map C to 4 as C's answer. Either they could have thought only one option is wrong, the other three are right, they might have not dropped this answer. This is one case. Or using the connect between these two information, they could have concluded Bell-Manford algorithm will be able to determine the strongest connected components in a directed graph based on topological sorting. That is an application of DFS. Overall, we go with option number 2 as the right answer. With this discussion, we are completing Unit 7 solutions.